Welcome back. In this video, we're gonna see what is an integral in calculus. Let me start with a problem that sounds simple and turns out not to be. You've got a curve, some wiggly line on a graph, and you want the area underneath it. Not a rectangle, not a triangle, where you've got a tidy formula, a curve. The shape keeps changing as you move along it. How much area is trapped between the curve and the horizontal axis? That question, area under a curve, is where the integral is born, and once you see how it's answered, the same idea turns out to unlock shocking amount of physical words. So stick with me because this one is worth it. So here is the thing that makes it hard. For a rectangle, area is just width times height. Done. But under a curve, the height is different at every single point. There is no one height to plug in. So the trick, and it's one of the great tricks in all of mathematics, is to stop trying to solve it in one shot and instead approximate it. Picture this. Take the region under the curve and slice it into a bunch of thin vertical strips. Now, each strip is almost a rectangle. It's got a flattish bottom and a slightly slanted top. But if the strip's narrow enough, you can just pretend the top is flat and treat it as a rectangle. Width times height. Do that for every strip and add up all of those little rectangles areas and you get an estimate of the total area. Rough, but an estimate. Now, the magic move. That estimate is off because the top of the rectangles don't perfectly match the curve. There are little gaps and overhangs. So what do? Now we make the strips thinner. More strips, each narrower. The rectangles hug the curve more closely. The gaps shrink. The estimate gets better. Thinner still, better again. And you push that idea all the way to its limit. Infinitely many strips, each infinitely thin. In that limit, the error vanishes completely and the approximation becomes exact. That's the integral. Is the exact total you get by adding infinitely many infinitely small pieces. Honestly, this clicked for me. It reframed the whole subject. Calculus stopped being formulas to memorize and became this one repeated idea. Chop something into tiny hits, then add them all up and take the limit. Let me show you the notation because it's actually beautiful once you know what you're looking at. The integral is written with this long stretch out S. And that's not random. The S is for sum because it's literally what an integral is, a sum. A sum of those tiny pieces. The people who invented this notation back in 1600s choose stretch S on purpose and is stuck around for 300 years. So you'll see something like the integral from a to b of f of x dx. So let's break every piece of that down because each part means something concrete. The f of x is your curve, the height of the function at each point. The dx is the width of one of those infinitely thin strips. Think of it as infinitely small changes in x. So f of x times d of x is height times width, the area of one tiny strip. And the long s out front, the long S out front says add up all of this. Then the little a and b at the bottom and top tell you where to start and where to stop along the axis. Read the whole thing out loud and it says sum up the area of all the thin strips from A to B. That's it. The notation is just the sentence I've been saying, written in symbols. Now, that version with a and b, start and stop points, is called the definite integral, and it gives you an actual number, a specific area from here to there under the curve. The answer is, say, 12, concrete. There is a second flavor called the indefinite integral, which has no start which has no start and stop points. And instead of a number, it gives you back a whole function. And to understand why that's useful, I have to connect integrals to the other half of calculus, derivatives. This is the part that ties the whole subject together. You might already know what a derivative measures. That a derivative measures the rate of change of something, how fast it's changing at each instant. The slope of curve a point. Here is the stunning fact, and it generally stunned mathematicians when it was nailed down. Integration and differentiation are opposites, inverse operations. One undoes the other. Taking derivative and taking the integral are like adding and subtracting, or like squaring and taking the square root, two directions of the same street. This is called the fundamental theorem of calculus, and fundamental is not an exaggeration. It says that if you want to find the area under a curve, you don't actually have to mess around with infinitely many rectangles every time. Instead, you find the function whose derivative is your curve, that's called the antiderivative, and the area falls right out of it. It connects two big ideas of calculus into one clean relationship, and it's the reason integrals are something you can actually compute instead of just admire. So an indefinite integral is really asking what's the function whose rate of change is this. Go backwards from the slope to original. Okay, let me get why any of this matters outside of a math class, because area under a curve sounds pretty niche until you see what a curve can represent. Here is my favorite example. Imagine a graph where the horizontal axis is time and the curve is your speed while driving. Now ask, what's the area under the speed curve? Watch what the units do. Height is speed, miles per hour. Width is time, hours. Height times width is miles per hour times hours, which is just miles. The area under a speed versus time curve is the total distance you travel. That's wild, right? A geometric area turns out to be physical distance, and it makes sense with the tiny strips idea. In each tiny sliver of time, distance is roughly speed times that little bit of time, and the integral adds up all of those tiny distances into in the total strip. And this generalizes everywhere. Anytime you've got a rate and you want the total accumulated amount, that's an integral. Flow rate of water into a tank, integrate over time, gives the total water. Electrical current over time gives the total charge. Force over distance gives you energy. The integral is the tool for accumulation, for adding up a change in quantity to find the grand total. Area under a curve was just the first, most visual version of a much bigger idea. So let me pull it all together. An integral is at its heart a sum. You take something, slice it into infinitely small pieces, and add them all up, and take the limit so the answer comes out exact. Geometrically, that's the area under a curve. The long S notation is literally spelling out sum of height times width. A definite integral with start and stop points give you a number. An indefinite one gives you back a function, and the fundamental theorem ties up to the derivatives by making integration the reverse of differentiation, which is what makes it computable. Then, out in the real world, that same operation is how you turn any rate into a total. If there's one sentence to walk away with, make it this: a derivative breaks up a whole into instantaneous pieces, and an integral builds those pieces back into a whole. They are two directions of the same idea, and that idea is the most of calculus. Here is what I actually do next if I want this to stick, because reading about integrals and feeling them are different things. Sketch a simple curve, a straight diagonal line. Even try the strips by hand. A few rectangles, then more skinny ones, and watch your estimate crawl toward the real area. Do that once with your pencil, and the infinite sum idea stops being abstract. That's the moment it becomes yours. I'm gonna end this video here, and I see you in the next video.